z squared. So this shows us a few things. It shows us, first of all, that what I've been claiming all along, which is that the notion of distance in a curved space, in a curved space-time, we can no longer ignore the curvature, which is when z is of order 1, doesn't have a unique physical meaning. We use two measures of distance, the angular diameter and the luminosity distance, both of which are perfectly valid measures in an ordinary flat Euclidean space. A perfectly good measure which we could use in this room and would give us the same answers. And here we say, yeah, they give the same answers so long as z is small. But when z becomes big, they become divergently different from one another. So that's showing us that the notion of distance as spatial distance between 2 points doesn't have an absolute invariant meaning in curved space. Okay, so it's demonstrating the point that I was making at the very beginning. It also says something else. It says that whether we use this or this, we're not actually gaining that much more information. In other words, it doesn't make sense to use both measures for the same objects. You should use whichever measure is best for the given object or given physical situation, since they only differ by a factor of 1 plus z squared. And z is something we can measure very accurately, so we're not going to get extra information by measuring both for the same object. So for the CMB, it turns out the useful measure is angular diameter distance. For other things, it'll turn out the answer is luminosity distance. And then thirdly, we have that for flat space, that's evaluated for flat space, the luminosity distance is just 1 plus z squared times the answer we had before, which was 2 over h naught times square root of 1 plus z minus 1 over 1 plus z to the 3/2. And that means when we expand this for small z, because of this 1 over here, we'll still get the same leading term. But all the higher order terms will be different because of that 1 plus z squared. So the expansion, so that means that the coefficient and how you interpret the coefficients in terms of the composition of the universe of these higher order terms will be different. But in a way which is easily calculable. So I think I left as a homework problem to work out what the coefficients are for this expansion. Okay, great. Now the only thing we need to know is what are the objects that we use for this test. For this test, instead of needing a ruler, what we need is what we call a standard candle, an object whose luminosity we know for sure. Okay? So, again, the history of standard candles and the history of this use of luminosity distance is a checkered history in cosmology. For basically the same reason as I mentioned before when I gave the example of largest galaxy in the cluster. Because the way we look for standard candles is we look in the nearby universe and we look for some phenomena, something which tells us what the absolute luminosity of objects are, and hopefully objects which all are going to have the same luminosity. Then we use those objects, assuming that distant objects of the same type haven't evolved, we use this law to determine the distance to them. But how do we know those objects haven't evolved? What independent means do we have of doing that? Well, the further out we go in redshift, the less information, the less independent tests we have. We can ask up to a certain distance, we're confident that it's a good standard candle, but how do we know when we go to yet larger redshift that we could trust it? And the history of cosmology for the last 100 years has been sort of betting on something that seemed good at short distances, using it at large distances, inferring something about the composition of the universe and the curvature of the universe, And then discovering from later measurements, no, we were wrong. There's an evolutionary effect we can't ignore. And we're still in that situation today. It's just that we have at least one standard candle, the Type 1a supernova, which, well, actually that's an interesting example. So Type 1a supernova are a certain class of supernova which, when observed locally, appear at first glance to have nearly the same luminosity. So they would have seemed to be good standard candles. And the nice thing about Type 1a supernova is supernovae are very bright when they go off, so you can see them at large distances. So you don't just need something which is good luminosity. It can't be too dim. You want to test it at large distances. It better be bright enough you can see it at large distances. So Type 1a supernova seemed to be, at first, a good candidate when measured locally. But actually, it turns out that's not really true. There are no, could you imagine that all Type 1a supernovae are going to have exactly the same luminosity? No, because there's different environmental conditions. So what you really mean is the variance in their luminosity should be small enough compared to the accuracy needed to measure the distance. So they're nearly the same. Well, it turns out they're not quite like that. Okay, there's some spread in their luminosity. But if you don't just measure their luminosity, but you measure their spectra. So Type 1a supernova brightens, has a certain combination of colors, and it becomes bright, and then it dims, and its color changes as it dims in a certain pattern. If you get that information on top of the luminosity information, then if they appear out to fairly large redshift, close to 1, to be, as far as we can tell, to be standard enough, given that combined information, to put them into different Type 1a supernovas into different categories, each of which I can use as a standard independently, and then use the combination as my standard candle set. And that's the state of the art today, out to a redshift of order 1. And from those measurements, those are far enough out, if you remember our expansion, maybe I still have it up. Yeah. When you get to order 1, this term begins to become important, and this term, in fact, the higher order terms begin to become important. You actually get, instead of a linear Hubble law, it begins to curve. And depending how it curves, it's telling something about the relative composition or acceleration or deceleration of the universe. And it's from that measurement that it was inferred that the expansion of the universe is accelerating. So by gathering enough supernova and using this combination of color, brightening and dimming, and luminosity as a standard candle, that was one of the first bits of information, first signs that the expansion of the universe is accelerating. It's an example of what we would call a kinematic measure, because we're measuring something directly about the expansion of the universe rather than its composition. It doesn't tell you what's causing the acceleration, it's just telling you that it's accelerating. Now, having said that, I should say also that the story hasn't stopped. Attempts to improve supernova measurements continue and push to redshifts between 1 and 2, at which point you don't have independent tests that tell you that they're standard candles. You're just assuming that the same standard candles that were standard at shorter distances are going to be equally standard at larger distance. Why would you expect it to be different? Well, because all kinds of things are happening in the universe around redshift 1. Formations of stars, the concentration of dust that would obscure light from the stars. If you have dust different in the past and the present, then the luminosity we'll observe will be different, just for that reason alone. So how do you know it's not dust obscuration that's messing up your story? So we don't know for sure just from these measurements. That's why in cosmology you cannot usually you can't just use a single kind of measurement to get a result. It's usually a campaign. The supernova campaign is a campaign to use supernova, but it only makes sense if I should say, trust but verify. Okay, it only makes sense if you can verify it by other techniques. Okay, so you should have a certain level of skepticism. When results come out using single technique in cosmology, listen, but don't bet on it. Have a certain level of skepticism. Anyway, these are examples of measures of the universe that, just examples of some of the measures of the universe to determine its composition and properties. And here's the story that, as we understand it today.